welcome back. In this lecture, let us review whatever we did in module 5 under phase equilibrium. As you know, there could be various phases. The three major phases that we are looking at in this particular course are the solid, liquid and the vapor phase, and if they exist in equilibrium or any two phases existing in equilibrium or all three phases existing in equilibrium with each other, how do we handle such situations is what we are going to look at, or what is the formalism for handling such situations is what we are going to look at in this course. We had initially seen the PT diagram, the pressure versus temperature diagram for a pure substance, to set the base for the kind of systems that we will be interested in. We said that in this region, and the region essentially means the combinations of temperature pressure, T comma P is each point here, the combinations of temperature and pressure in which the solid would exist, in which the liquid would exist here, and here the vapor exists. This is the sublimation curve across which the solid to vapor transition takes place, which means along these combinations of temperature and pressure you have solid coexisting with vapor, and this is the vaporization curve. It is easier to imagine. We have the liquid coexisting with the vapor across this line or across the pressures and temperature conditions that are given by this line, and this is the fusion curve across which or on which you have coexistence of both the solid phase and the liquid phase. We also said that beyond or above the critical temperature, critical pressure point is this, above the critical temperature here and above the critical pressure we have the supercritical phase, which we are not going to consider in this particular course. The same information can also be obtained in a P versus V diagram, the pressure versus specific volume diagram. This is again for a pure substance, and we saw that regions in the earlier curve or earlier graph get represented as the lines in the previous graph get represented as somewhat as regions in this particular graph. Here we have the solid phase in these combinations of specific volume and pressure. In these combinations of specific volume and pressure you have the liquid phase, and in these combinations of specific volume and pressure we have the vapor phase. This is the critical point here, Vc Pc, and in this region we have the coexistence of both the solid and liquid phase. In this region we have the coexistence of solid and vapor phase, and underneath this dome in this region we have the coexistence of liquid and vapor phases. So these are the kind of systems that we are looking at. We have the coexistence of two or more phases together at the same time, and initially we looked at the pure substance and then extended it to a multi component system. The take home message from this particular module is this exact slide. The conditions that thermodynamics provides with for as criteria for different phases to exist in equilibrium. As we had seen, before we look at the conditions, we need to understand that it is a dynamic equilibrium, which means that there are changes occurring at the micro scale, and those changes occurring at the micro scale balance each other so that there is no change at the macro scale. We had given the example of a substance going from the liquid phase to a vapor phase. For example, water, just pure water, going from the liquid phase H2O that we know of to the vapor phase, and we said that there is a rate at which the water molecules move from the liquid phase to the vapor phase, and at the same time there is a rate at which the water molecules move from the vapor phase to the liquid phase. if the rate in one direction equals the rate in the other direction, that is the condition of equilibrium that we are looking at. And what we mean by dynamic equilibrium is that these are taking place all the time. It is just that the rates balance, so that we are not able to see any changes at the macro scale. We said that we are going to indicate phases by alpha, beta, gamma and so on, and there could be multiple phases of the same kind, such as two distinct liquid phases and things like that. Now, and also the components we are going to be we are going to indicate by 1, 2, 3 and so on. And now we come to the criteria for thermodynamic equilibrium. If a system is said to be in thermodynamic equilibrium, it needs to satisfy simultaneously the following equations, that is, T of the alpha phase must equal T of the beta phase must equal T of the gamma phase and so on. Therefore, the temperatures in all the phases must be equal. Equation 5.1, this is the condition for thermal equilibrium. P in the alpha phase, the pressure in the alpha phase must equal P of the beta phase must equal P of the gamma phase and so on. The equality of pressures across the various phases, equation 5.2, the condition for mechanical equilibrium. This is thermal equilibrium, mechanical equilibrium, and the condition for chemical equilibrium is given by all these equations that follow, which is the chemical potential of any component in any phase must be equal, or in other words, the chemical potential of a certain component I in all the phases must be equal. In other words, mu 1 alpha, which is chemical potential of component 1 in the alpha phase, must equal mu 1 beta, must equal mu 1 gamma and so on. We call this equation 5.3. Mu 2 alpha equals mu 2 beta equals mu 2 gamma and so on. This is chemical potential of component 2 in the various phases alpha, beta and gamma. They must all be equal, equation 5.4, and we wrote one more equation, and then we said we need to write as many equations as there are components. For the third component, mu 3 alpha equals mu 3 beta equals mu 3 gamma and so on. This was equation 5.5, and we could write as many equations as there are components. So, all these put together are the conditions that need to be simultaneously satisfied for chemical equilibrium. Thermal equilibrium, mechanical equilibrium, chemical equilibrium, all three put together is thermodynamic equilibrium. Then we derived what is called the phase rule for non-reacting system. There are no reactions in the systems that we are going to consider, and for such systems this phase rule will be valid, and the basis for this was something like this. If the system contains pi phases, solid, liquid, vapor and so on, or it could be liquid 1, liquid 2 and so on and so forth, and if the number of or for simplicity let us say solid, liquid, vapor phases, and the number of components in each phase is C, then we said that the number of variables needed to specify the state of the system is pi into C plus 1. This is the number of variables, and we saw that the number of equations between the variables by the arguments, you can go back and see the arguments again, is pi minus 1 into C plus 2. Therefore, the number of variables, number of equations between the variables is pi minus 1 into C plus 2, and the number of variables was pi into C plus 1. We know that for a set of mathematical equations, if there are certain variables and certain equations, the number of variables is typically equal to or more than the number of independent equations between them for a meaningful solution to arise. If it is equal, fine, we have a unique set of solution. If it is not equal, probably we need to supply some information so that the number of variables becomes equal to the number of equations, and then we can get a unique solution. This was the basis for the phase rule as follows. This is the number of variables pi into c plus 1 must be greater than the number of equations pi minus 1 into c plus 2. In other words, if you multiply and then group these appropriately and transpose this, we saw that c minus pi plus 2 must be greater than or equal to 0. If it is equal to 0, we get a unique solution set. If it is greater than 0, then we need to supply that many variables, or we need to specify that many variables for a unique solution to arise. And the number of variables that we need to supply is what we designated as the number of degrees of freedom, or f equals c minus pi plus 2. This is called the phase rule. The number of separate variables that need to be specified to completely describe or completely specify the system or any given system is called the number of degrees of freedom of that particular system. And typically the variables that we choose are pressure, temperature and specific volume in that order of importance, or temperature, pressure, specific volume. This is worth repeating. Application of the phase rule tells us that the number of independent variables that are required to completely specify the state of a system if the number of phases and components are known, pi phases and c components, f equals c minus pi plus 2. And again, this is valid when there are no reactions that take place in the system. Then we worked out an example to calculate the degrees of freedom in a couple of systems, and then we looked at the so called Clausius-Clapeyron equation. To remind you, the Clausius-Clapeyron equation is valid for any two phases in equilibrium. It could be a solid liquid phase, a liquid vapor phase, solid vapor phase, and so on and so forth. These are three combinations that are possible, and the vapor solid, the solid liquid and the solid vapor phase, they should be two distinct phases actually. And we went about deriving the Clausius-Clapeyron equation by using the condition that those two phases are in equilibrium, and therefore the chemical potentials have to be equal. That is where we started, and then we expressed the differentials of the chemical potential, or equated the differentials of the chemical potential, and we expressed them as functions of temperature and pressure because they are easily measurable. And then we took a detour to essentially get expressions that are useful for the temperature derivative of the chemical potential and the pressure derivative of the chemical potential at constant pressure and temperature respectively. We also got one more equation that was useful. This is the way we went about doing it. We started with the equation 215. We applied the reciprocity relationship between two of these things taken together. I think we took these two first and then these two to get dou mu I dou p at constant T n I as dou V T dou n I at constant T p n j, and this by definition became the partial molar volume of the component I, and dou mu I dou T at constant P n I became minus dou S T dou n I at constant T p n j, which by definition is the partial molar entropy of the component I, the negative of that. We got this, and then It was quite interesting when we went about the derivation, and this was the additional equation that we got, dou mu I by T dou T at P n I equals minus H I T hash by T squared. This we will use later, is what we said, and those were equations that are valid for multi-component systems. And since we are looking initially at pure components while deriving the Clausius-Clapeyron equation, we wrote equivalent expressions for the pure components. Dou mu dou P at constant T equals the partial molar volume becomes the molar volume here V. Dou mu dou T at constant P became the molar entropy minus S, or minus of the molar entropy minus S, and this was the additional expression that we had, dou mu by T dou T at constant P equals minus H by T squared. And using these we substituted into the equality of the chemical potential differential expression, which is phi 10, which is given here, dou mu alpha dou T at constant P dt plus dou mu alpha dou P at constant T dP equals dou mu beta dou T at constant P dt and dou mu beta dou P at constant T dP. And when we substituted these, we could write this in terms of molar entropies and molar volumes, and just by rearranging that we could get d dt of P is the difference in entropies divided by the difference in specific volumes. And then we had utilized the condition or the special case that the transition between the two phases, between the liquid and vapor phase, that process can be considered to be a reversible process, and therefore we could apply the second law statement for writing entropies in terms of the heat interaction Q reversible by T. And since the only heat interaction is going towards the change of phase, we could replace that with the change in enthalpy between the two phases, and which is nothing but the latent heat of the phase transition, in this case latent heat of the phase transition between alpha to beta, given as L by T, and therefore we could write dP dt equals L divided by T delta V. This was the Clausius-Clapeyron equation, where delta V, the volume change during the phase change, is V alpha minus V beta. And then, as mentioned earlier, Clausius-Clapeyron equation is valid for phase changes, for any phase change, not necessarily liquid vapor, it is also valid for liquid vapor phase change, and it can be interpreted as the change in pressure per unit change in temperature that is needed to maintain phase equilibrium. And then we brought in this approximation that for vapor liquid equilibria or vapor solid equilibria, the difference between the vapor volume and the liquid or the solid volume, or rather the I should say that the liquid volume or the solid volume is negligible compared to the vapor volume. Therefore, the difference between those specific volumes is nothing but equal to the vapor volume itself. Therefore, delta V is approximately equal to the vapor volume of the vapor volume or V gas, and if we use an ideal gas relationship, we can write that as equal to RT by P, and if we do that, we get d ln P dt is approximately equal to L by RT squared, which is a good approximation to use for the Clausius-Clapeyron equation as long as the vapor pressure P is not large. This is what we had said. Then we worked out a problem involving isopropanol, our popular substance, which is going from the vapor phase to the liquid phase. The solution was detailed. We had to, it was quite simple, we had to find dP dt, and we said that we could find that by using the values of these variables. L and T were given in the problem itself. and delta V was the one that we needed to find out. It turned out to be a little lengthy because it involved an iterative solution for both the volumes, and I had shown you how to set up an iteration in a standard spreadsheet and go about getting the value. It is a very simple way of doing that. Once you set it up, it is simple, it just takes time to describe it, but the process itself, if you do it yourself, is quite fast. And we saw that we had used different formulations of the Redlich-Kwong equation to get estimates of first the vapor volume by starting with the ideal gas volume as the initial guess, and then a different formulation for the liquid volume, in which we started with the value of B as the initial guess, the volume of molecules as the initial guess for liquid volumes. Then we started looking at the various equilibria, or the specific governing equations for various equilibria. We had looked at vapor liquid equilibrium in some detail. The basis is quite simple, the temperatures and pressures have to be equal, and the chemical potentials have to be equal. We said we are going to take these as given, that is thermal equilibrium and mechanical equilibrium is given, and we will typically concentrate on the chemical equilibrium part, is what we said. Mu V equals mu L is what arises as a part of writing the chemical equilibrium in the liquid vapor equilibrium case. And then we had, if it is a pure substance, we said we could write mu V as mu naught plus RT ln Fv, and mu L can be written as mu naught plus RT ln Fl. So cancelling the terms, we could get Fv, the fugacity of the pure component in the vapor phase, must equal the fugacity of the pure component in the liquid phase, and we said that must say equal F sat, because saturated conditions exist when there is a liquid to vapor or a vapor to liquid transition. And using the fugacity coefficient and the fact that the pressure would turn out to be the saturated pressure, we could write phi V, which is the fugacity coefficient of the pure component in the vapor phase, times P V equals F sat, or phi V is nothing but phi sat, and P V, as we said earlier, was P sat. This can be written as equal to F sat, and this was for a pure component, phi sat P sat equals F sat, and for a multi component system we used the equality of the chemical potentials of the component in the two phases, and we could write Fi V hat equals Fi L hat, and then using the detailed expressions of the chemical potential, mu I equals mu I hash plus RT ln phi I yi, which could also be written as mu I naught plus RT ln phi I p yi. This is for the vapor phase, and this is for the liquid phase. Mu I equals mu I hash plus RT ln gamma I xi, which is mu I naught plus RT ln gamma I Fi xi. Fi is the pure component fugacity, and we equate the two, then we could write phi I p yi equals gamma I Fi xi. This is the condition for equilibrium in the vapor liquid equilibrium case. This was equation 530. Then we worked out a problem which involved KLa, the volumetric mass transfer coefficient, and the solution was quite simple, that is the chemical potential of oxygen in the vapor phase must equal the chemical potential of oxygen in the liquid phase under the conditions in the problem, which is that of equilibrium. Then we looked at using the vapor liquid equilibrium case and estimating the fugacity coefficient from the PVT data at equilibrium, which is the vapor liquid equilibrium. This was essentially a different method of getting the fugacity coefficient. We had derived this by starting out with some expressions in module 3. We got RT d ln f equals VdP, and we had integrated that expression, and we had identified that the molar liquid volume B is a weak function of pressure at temperatures below the critical temperature, and therefore this V molar volume can be considered a constant in this integration. It comes out, and that is a very good approximation. If it comes out, then we could write ln of f by f sat equals VL, and then the integral will, the definite integral between P sat and P1, we are going to drop 1, becomes P minus P sat by RT, or f by f sat equals what we call the Poynting factor exponential of VL, the molar liquid volume, P minus P sat by RT. And then we had invoked equation 528, phi sat P sat equals f sat in the case of vapor liquid equilibrium, and we could write by expressing one in terms of the other and recognizing that phi is nothing but f by P. We could write phi I P y I equals gamma I f I x I. This is the condition for equilibrium in a multi-component system. This was for the pure component. We could write fugacity as phi sat P sat exponential, this is the Poynting factor, and then for a multi-component system this is valid as what we saw earlier in equation 530, and when we used this expression for Fi that we had developed, gamma I into Fi, which is given as phi I sat P I sat exponential of VIL P minus Pi sat by RT, this is Fi times the mole fraction Xi, and we call this a phi, phi I P y I equals gamma I Pi sat Xi. This is the useful equation in this particular case for estimating the activity coefficient, where phi I we had said was nothing but phi I by phi I sat exponential of minus VIL P minus Pi sat by RT, and we also recognize that for most biological systems at at pressures that are normal, this term pretty much becomes 1, and therefore phi I becomes phi I by phi I sat, and therefore could substitute it back into this to get gamma I from VLE data. VLE is vapor liquid equilibrium data. And we also saw that phi can be estimated from the second virial coefficients. We did not derive this, I just said that I am going to give you expressions so that you can rather you could use this in the if these values become available in terms of tables and so on. Okay. Then we went about deriving the governing equations for solid liquid, liquid liquid and solid liquid equilibria. In fact, you derived this and we just checked it, and the basal equations that we used were the conditions of thermal equilibrium, mechanical equilibrium and chemical equilibrium, predominantly chemical equilibrium, and we had seen where this becomes relevant. In the case of liquid liquid equilibrium, we said that you could have two different liquid phases of one being hydrophobic, the other one being hydrophilic, or both could be hydrophilic. The hydrophobic hydrophilic pair is used in, say, antibiotic extraction. The hydrophilic hydrophilic pair, two distinct hydrophilic phases, is used in the extraction of proteins, because to maintain their activity by maintaining their conformation, what we had seen. And if L1 and L2 are the two liquid phases in equilibrium, and for each component we could write the equality of chemical potentials, and from this expansion comes the equality of the fugacities of the component I between these two phases. And utilizing equation 4.8 in module 4, you could write the fugacity in terms of pure component fugacity, gamma I activity coefficient in the L1 phase, Fi the pure component fugacity, times the mole fraction of I in the L1 phase must equal gamma I in the L2 phase pure component fugacity times Xi in the L2 phase. So, this is the governing equation for liquid liquid equilibrium. It also worked out a problem after this, an example that of ampicillin extraction and the ratio of the activity coefficients in those two phases. Then we looked at solid liquid equilibrium in some sort of a hurry. We said that you could have a solid phase and a liquid phase, and let us say a component distributing between the solid phase and liquid phase in equilibrium, and given some examples such as biosorption. For example, when there are toxic trace metals that are present in, say, an effluent, one of the ways by which they can be removed effectively is by contacting the liquid phase with the metal. You contact this liquid phase with the metal with another solid phase into which the metal can partition. Therefore, there is a huge reduction in the volume that contains the metal, and therefore better processing capabilities later. The solid phase could be let us say dried cells, dried cells from even brewing industries could be used as the material which can be utilized to remove the toxic trace metals such as chromium, copper, cadmium. Chromium, as you all know, is quite toxic. Chromium 6 is very toxic, and so on. So, this can be used to remove all such things. Bioleaching is a similar phenomenon where there is contact between a solid and a liquid phase, and there is distribution of a metal, say, between these two phases. And even in some analytical steps, you come across situations where a solid is contacted with a liquid and there is distribution of a certain component or some components. In such cases, we could utilize the same arguments for equilibrium. Equations 5.1 to 5.5 and so on need to be valid in any case. They are basal conditions of equilibrium. Even if we concentrate from 5.3 onwards, we are going to take thermal and mechanical equilibrium as given. The chemical equilibrium, the equality of chemical potentials of each component across the phases, of a certain component across phases. So, if we use that, then we come across the condition that the chemical potential of the component I in the solid phase must equal the chemical potential of the same component in the liquid phase. This could be, for example, chromium or cadmium that is distributing between the wastewater and the biosorbent that is used to remove this particular metal. So, mu I in the solid phase equals mu I in the liquid phase, and if we take that into account and expand it in terms of the fugacities, the terms will cancel, and what we are left with is the fugacity of the component I in the solid phase FIS hat equals the fugacity of the component in the liquid phase FIL hat. And in terms of the activity coefficients, we can write for the solid phase gamma IS, the activity of the component I in the solid phase, the pure component fugacity in the solid phase, times the mole fraction in the solid phase Zi equals the activity coefficient in the liquid phase times the fugacity, the pure component fugacity, times the mole fraction in the liquid phase. and this becomes the governing equation for equilibrium in the solid liquid case. Zi and Xi are mole fractions of component I in the solid and liquid phases respectively. So, we had essentially seen the conditions of equilibrium, chemical equilibrium particularly, and then phase rule, and then we had taken up specific cases of vapor liquid equilibrium VLE, liquid liquid equilibrium LLE, and solid liquid equilibrium SLE. And we had also shown one of the ways of estimating the activity coefficient from the conditions of vapor liquid equilibrium. That is essentially what we did in module 5, and when we come to the next class, we will start out the last module of this particular course, module 6 on reaction equilibria. See you then.